Hello, good day class, I'm here again. Now we are actually on to what? Electric field part 2. Now we are going to be looking at the properties of these field lines. As I said from the previous class, I said that what? Field lines are imaginary lines. They are imaginary lines, and we talk about what? The charges. We said that we have the positive charge and we have the negative charge. Now we're going to be looking at the properties. Now from what I actually say, a recap. I said that what? Like poles, you can have negative and negative too. They will what? Repel. And what matters is the direction. So we're going to be using these to what? Explain the properties of what? Of electric line, field line. Just understand this and you are good for explanation. Okay? Now we said that what? Unlike poles, we what? Attract. We attract. Sorry. Let me increase my. So we attract. Let me increase this. We have positive and negative. I want to be very fast so that we're going to be moving into a very good. So this gives out still. Please, the direction matters a lot. It's giving out. Why this one is what? Taking in. The electric field lines is terminated in what? In a negative charge. Now, one thing you need to understand here is that what? You notice that what? The electric field lines, they are not crossing each other. They are really isolated. See, let me draw a what? A isolated charge. We have this. Have you seen? They are not crossing each other. They can't cross each other. That's one of the properties that we actually know. They don't cross each other. As you can see, it's not crossing the next line. This one is not crossing the line. They are really isolated. So one of the properties we have that what? They do not what? Cross each other. They do not cross each other. That's one of the properties. The electric field lines don't cross each other. Now let us look at another one of the properties that we know. We say that what? They are originated from the last class. Originated from where? The positive charge and terminated as negative charge. That's what you notice. They are originated from the positive charge and terminated at the what? Negative charge. From what I explained. Now, another thing again is that what? They are perpendicular to the surface of the spherical charge. I will explain. They are perpendicular. They are perpendicular to the surface. Please write it down. Of the what? Spherical charge. Now, as you can see here, look at it. This is the surface of the spherical charge. A charge is like this. They are perpendicular to the surface. Normally, there's something we call tangents. Now, if you look at this tangent, it's moving like this, right? It is perpendicular to the what? The surface. This electric line of force is perpendicular to the what? Surface of the what? Electric charge. So that's what they mean here. They are perpendicular to the surface of the electric charge. And we want to look at the last one. Now, for an isolated charge, for an isolated positive charge, what happens? We say that what? For an isolated positive charge, you can see it's giving out. So meaning that what? The electric field lines move from an isolated positive charge to what? Infinity. It gives out. So you write it that what? The electric charge, for an isolated positive charge, the field lines terminate at infinity. For an isolated positive charge, the field lines terminate at infinity. We have it as this. It terminates at infinity. Now we have that what? For an isolated negative charge, the field line, the field line terminates. Okay, the field line originates from what? Infinity. For an isolated positive charge, meaning that what? Something we have here, it terminates at infinity. It's going. It's just giving out. While for an isolated negative charge, it originates from infinity and terminates at a particular point in the charge. It originates from infinity and terminates at a particular point in the charge. So we can see that well, these are the properties of field lines. We have that well, they do not cross each other. You don't need to cram, please. That's why I'm drawing, I'm explaining it. They do not cross each other. They originated from what? The positive and terminates at the negative charge. They are perpendicular to the surface of the spherical charge. For an isolated positive charge, the field lines terminate at infinity. While what? For an isolated negative charge, the field lines originate from infinity and ends itself at a particular point in the charge. So we're going to be looking at electric force, because we said that what? Electric field lines. We said that what? Electric field lines is being experienced, is a region of space whereby what? Electric force is experienced. Now, you will be asking me, what is electric force? What is that force? What is that force? Now, you know that your force is what? A mass times what? Acceleration from what you all know. But in this case, we are going to be looking at a person. We are going to be looking at a law. We call it what? Coulomb's law. To explain this force. Coulomb's law. Now, Coulomb's law is different for coulombs. Note, students always try to put it together. Coulomb's law is different from coulombs. When you think about coulombs, coulombs itself, which is C, is the unit for what? Charge. Is the unit for what? Charge. Are you getting me? So when you explain what is charge, charge is equals to what? IT, which is the product of the what? Electric current flowing to the what? The rate at which the what? The electric current is flowing. I wouldn't say that the rate, the product of the electric current flowing times the what? The time taken for it to flow. So we have it as what? Charge. Now it's different from what? Coulomb's law. When we talk about Coulomb's law is divided into two parts. We have the what? The product law and the inverse square law. It's divided into two parts, although I'm going to combine it later. Now let us look at the product law. What's the product law of coulombs? What is it saying? What is it trying to state to us? It said that what? The force states that the force of attraction and what? Repulsion. Please, it's not the force state. The force state that. No. The force of attraction and repulsion, because of what? This is the two things that we'll be dealing with. We are going to be looking at all the attraction part and the repulsion part. For gravitational force, we said that what? The force of attraction alone. But for this, we are going to be looking at what? The force of attraction and what? Repulsion. The force of attraction and repulsion is directly, from your observation, proportional to the products of the two charges. Now, what are we trying to say mathematically? It says that what? Your F, force of attraction and repulsion, is directly proportional to what? Q1 and what? Q2. Please, I want you to note. Force of attraction and repulsion is directly proportional to Q1 and Q2. Now, in variation, which I used to explain to mathematics students, or further math student, that whenever you see something like this, it means that what? The higher the charges, the higher the force of attraction and repulsion. The higher the charges, if the charges is 10 microcoulombs, and you have what? 10 microcoulombs again for Q1 and Q2. You can't compare the force that will exist between these two and the force that will exist between what? 2 coulombs and what? 3 coulombs. This one is micro, very small charge. So you can't compare the force that will exist between these two. The force that will exist here will be high, while the force that will exist here will be what? Very small. So you should understand when we talk about what? This product law. We said that what? The force of attraction and repulsion is directly proportional to the product of the two charges, meaning that what? If the two charges are high, the force of attraction will be high. If the two charges are low, the force of attraction will be what? Low. Now let us look at what? Inverse square law. Now for inverse square law, we state that the force of attraction and repulsion, please, I want you to write, is inversely proportional to the square of the distance r between the two charges. What are we trying to say mathematically? Because we're going to combine them together, so you should understand. So we have it that what? F of attraction and repulsion is inversely proportional to the what? Square of the what? Distance r between the two charges. So the higher the what? If you look at it, if you have a distance, a charge like this, positive charge and a negative charge, and you have a positive charge and a what? Negative charge. Now the force of attraction here will be R, because of what? They are closer than the force of attraction between these two. So meaning that what? The distance actually varies.
So if this force of attraction is very high, so you look at what? The distance. The distance is very small. So if the force of attraction is very small, what happens to the distance? The distance is very what? High. So you should understand that what?
Inversely proportional. So the next class we are going to be looking at what? The combination of these two laws to actually state Coulomb's law. We are going to state Coulomb's law and see some calculation. So thank you. I will see you in your part 3 of